Thank you very much.
Thanks so much, Chris, for getting us off to a great start. So next, another fantastic colleague, Bruce Guthrie from University of Edinburgh. Bruce leads the CISC, and he'll be talking about some of the many data challenges that there are. So Bruce, over to you. Thank you.
Thank you. Okay, so I was going to talk, really narrow. That's a very broad overview. I'm going to go for something really narrow and specific, which is how do you define conditions? And it's so through a glass darkly. A lot of this is you're kind of trying to stare at the data through a piece of smoked glass suitable for looking at the sun. So what's the big challenge? I mean, the big challenge is that what we have is a really imperfect record of what happened. So we're using routine data. It's what's recorded in various different kinds of records for various different kind of purposes in various ways in different settings. And so, what we really want to know, we want to know exactly what happened and when it happened. And so you can imagine a timeline here. So if this arrow is an individual's life, this is a person diagnosed with hypertension. And so we have ways of saying that someone's got hypertension. We've got a first date. We can say, yes, they've been diagnosed with hypertension. But then, they also get diagnosed with type 2 diabetes. And so these are both completely voluntary diagnoses. They're not driven by events. They're driven by testing and measurement. And so if you never go to the doctor, you're never going to be diagnosed, or at least you're going to be diagnosed later than if you go to the doctor all the time and someone is measuring things all the time. And these are things where one thing prompts the other. You're diagnosed with hypertension, someone measures your blood sugar. You're diagnosed with type 2 diabetes, someone measures your blood pressure. And so when we're thinking about trajectories, we're very often thinking, oh, yes, this came first and then this happened, so this might cause that. But actually, often these are arbitrary orders, and the timing is rather arbitrary because it kind of depends, but it's quite difficult to model that. It's quite difficult to fully understand that. And so we're really interested in timing and sequencing, but actually the data may not be granular enough to do that. You might be able to say these things happened at around the same time in the same quarter, but you wouldn't necessarily say that one truly preceded the other. There's real issues with granularity. So, what level of granularity do we want to work at? So the same person acquires a code in Valerie Kwan's terms of, coronary heart disease unspecified, and then gets stable angina, and then gets a myocardial infarction. Are these different things, or are they all just atherosclerotic heart disease? And if you had stable angina, then that probably what you had when you had unspecified CHD. It just wasn't coded that way. And it wasn't that stable because they had an MI quite soon afterwards. So, what level of granularity do we want to work at? And often, if you're working at really granular levels, then you end up double counting stuff. This is all the same disease process. And so if you're interested in causation, why should you be grouping these things together? If you're interested in prediction, then actually having all the codes might be better for prediction. And then finally, the issue of kind of, are you willing to overwrite the past? So this person with type 1 diabetes now has a code for type 2 diabetes. Well, what kind of diabetes do they actually have? And so at any one moment, we can draw a line through this timeline and we can make a decision about what the person has at that moment. But let's say that, you can dig into type 1, type 2 diabetes. You can use prescribing data. You can use other data to try and decide which one it is. Well, what happens if you decide that it's actually type 2, but the first record is type 1? And are you willing to overwrite that data when you're using it? As an example of that, two kinds of cardiomyopathy. Well, you're pretty unlikely to have both. You're pretty unlikely to have dilated if you've got hypertrophic. These things don't really go together. So how do you decide what's the truth? And if you decide that the later one is the truth, does it overwrite the earlier one? And so the way, well, what does this actually look like in data? So this is overlaps in diabetes data. So on the left is if you're looking for type 1, type 2 diabetes and GP data, on the right is hospital data. So the hospital data mostly just says diabetes. It doesn't specify type at all. And you get these, in diabetes, there is a small overlap between type 1 and type 2. I should say that's a clean overlap because that's not the raw data. But once you even actually tidy it up, you still get overlaps. And if you look at cardiomyopathy, well, actually, most people with cardiomyopathy are diagnosed with other cardiomyopathy. And that's because the commonest code is cardiomyopathy not otherwise specified. And so although in theory, you can get really granular diagnosis, actually the way that we code is we often code at the highest level. And so you can't really get granular. And if you go for granular, you then get these troubling overlaps that you need to deal with. So what do we currently do? I mean, I think, you know, reflecting this, when we do really focused studies of something, we spend loads of time trying to define the outcome and key predictors. And then if you've got other variables, you tend to just reach for off-the-shelf stuff measured with less precision, less accuracy. Whereas in if you're doing multiple long-term conditions research, everything is meant to be equally important. So you're meant to spend as much time on every single condition as you would in a focus study. And that's really, really hard to do. You know, the amount of time you need to do this is quite extreme. And so I think we've tended to revert to off-the-shelf code lists and then fiddle around with them. And I'm kind of guessing the other consortium have done something similar. But the really important choices about how granular are you going to be? And then whatever you decide, you've got to include, what are you going to do about overlaps? So if you're interested in clustering of conditions, what do you do when your data is full of spurious overlaps? And so in HDR UK phenotype prognostic atlas, for example, one of the commonest comorbidities of type 2 diabetes without complications is, of type 2 diabetes with complications is type 2 diabetes without complications. Because they did have that in the past, and now they've got complications. But if you just look for an overlap without having a rule, you say, oh, they've got both. But you can't have both. You can have one and then the other. And I think there's often no real consensus about how to manage these. And the overwriting issue, I think, is particularly important. Longitudinal phenotyping is really hard, and I'm really not sure that we've cracked that. And so if you're interested in prediction, you might just say you've got to take the data as it is, because that's what you would know at the time. But if you're interested in etiology, you ought to be overwriting, because you want to be accurate about what people actually have. And so what do we need? I mean, I think phenotyping at a single point in time, cross-sectional data, actually, that's really come a long way. And I think we could all say that works quite well. There's lots of published code lists. There's issues for overlaps, which I think that's in the infancy compared to code list work. But longitudinal phenotyping, I mean, I just think we've got a long way to go with that. But actually, if we're really serious about examining trajectories, then we do need to have much better ways of trying to deal with longitudinal phenotyping, including how much overwriting are you willing to do in the history because of information that you know later on. Thank you.